Thank you for that, Xingling. Really appreciate it. And good morning, everybody. Good morning, everybody. Look, it's a real pleasure for me to be here. I'm very pleased that I was invited to speak. I get to talk about my favorite topic in the world, the automotive industry. And I've got to tell you, I've covered this business for an awful long time, many decades. And I've never seen the situation that the industry is in today, and that's what I want to talk about. I'm not going to talk a whole lot about coatings, because I found a long time ago that if you're speaking to experts, they're the experts, not me. But I can give you some ideas of what's going on in the industry right now. And I also have to mention, before I kick that off, congratulations to the Coating Society. 50 years is an incredible accomplishment. And that tells me two things. Number one, you all support it. You see value in it. And obviously, you play a real value-added role for the industry. Otherwise, you wouldn't have been around for 50 years like you are. What I want to talk about today is where the industry stands and looking to other things in the future that could be solutions. But here's the situation that we're in right now. The automotive industry is not growing. I'll say that again. The automotive industry is not growing. And this is true all around the world, whether you look in the United States, in Europe, in Japan, in South Korea, in China. It's not growing. Automakers, by and large, the legacies are not growing. Bad U.S. government policy on both sides of the aisle have burned up tens of billions of dollars of investments. The tariffs are causing chaos throughout the entire supply chain and raising costs. Warranty and recall costs in this industry have skyrocketed. You know, every year the National Auto Dealers Association publishes what car dealers in the United States have earned in terms of warranty work. Last year it was $30 billion, warranty and recall. And guess what? In the last 5 years, that's up 78%. It's crazy, and it's largely going underneath the surface. So market share right now is more important than ever. I'll get into more of that. And automakers need fresh new products that really grab the public's attention, but they need to do it with minimal investment because of all the tens of billions of dollars that have gone up in smoke in EV investments and the added costs of tariffs and the growing costs of recalls and warranty. It's enough to set your hair on fire, but don't panic. This is what we do in the automotive industry. We always confront very hard problems head on, and we start chipping away at them. And we chip away at them every single year and keep on doing that until it gets resolved. And it does get resolved, but the nature of the industry is some other issue then comes up. But there's nothing wrong with this automotive industry that cannot be fixed with great product. Great product fixes everything. Believe me, it addresses market share, it addresses the bottom line. And the work that you all play or the work that you all do can play a decisive role in this. But let's get into a little bit more of what I'm talking about. The auto industry isn't growing. Maybe you've heard this term before, peak auto. Automotive sales globally peaked in the 2016 to 2017 time frame. And they've been going down ever since. Here is a line graph of U.S. auto sales over the last 10 years, 2015 to 2025. If you look at the left-hand side of the chart, it's higher than the right-hand side of the chart. And in this time, by the way, the population of the United States grew by 25 million people. 25 more million people in the country, and we're selling fewer cars and trucks and vans than we did a decade ago. In fact, you could take this back to the year 2000. 25 years ago plus now, we were selling more cars in this country then than we are right now. The situation is worse in Europe, it's worse in Japan, it's worse in South Korea, and this is what is a shocker to most people. The Chinese domestic retail market is not growing. It's bouncing around 22 million a year, which is a nice number, but it's not growing. So In the US, certainly, I think a huge thing that's driven this plateauing of car sales is peak pricing. And you can see on the chart on the right-hand side, that's when COVID hit, and kablamo. Prices of cars shot up 30% in a very short amount of time. We have priced millions of households out of the new car market. They simply can't afford it. Now, I guess in a way, maybe the good news is there's plenty of really good used cars out there. In fact, cars coming off lease, they're 3 years old. Lots of them don't have a lot of miles. They almost look brand new. And that's what's taken up for those people who cannot afford to get into the new market. But there's a lot of upside potential if the industry can crack the code and make cars more affordable. The percentage of Americans buying new cars has decreased. So the blue lines are sales. The sort of orange line is the percentage of Americans who went out and bought a new car. The peak, by the way, when more Americans went out and bought a new car than at any other time as a percentage of the population, was 1978. 1986 was also a good year, and those are the two peaks that you see in that orange line, and it's been pretty much downhill ever since. And at this point, you know, if the same percentage of people bought a new car that did in the year 2000, last year we would have not sold 16.2 million new vehicles. We would have sold 22 million more new vehicles. And guess what? That's the same number as China. So we have the opportunity to make the US market as big as the Chinese market if we can crack the code and get more consumers to come back into the new car side. But there's a demographic time bomb here. The baby boomer generation, of which I am a representative, was 76 million people. Gen X, it dropped down. Gen Y, which are the children of the boomers, went up a bit. Gen Z, it started dropping again. Gen A. Gen A is 0 to 15 years old. Sometimes they call them, they call them Generation A. 25 million fewer Gen A than the boomers. So take that out another decade or so, where the leading edge of Gen A is going to be in the car buying market. There's 25 million fewer of them. You think this industry is going to grow? It's going to go back to the great old days of selling 17 to 18 million cars a year? I don't think those days are coming back. And so we also have to look at the car companies. You know, GM and Ford have just reported their earnings, Q1 earnings. Ford did it last night, GM did it earlier this week. And the media is like, oh my gosh, they're putting in strong performances here. Their revenue and their profits look a whole lot better. But what I did is went and inflation adjusted the top line, the revenue line. And here's GM. The blue line is GM's revenue growth. And you see it really took a nosedive during COVID, and it's come roaring back until you inflation adjust those dollars back to 2015, and guess what? GM, on an inflation adjusted basis, has not grown at all. Ford's even a little worse. Ford's lower than what it was 10 years ago. So you got to look behind the headlines of what the media is reporting on these latest financial numbers. I'm going to argue that these companies are not growing on an inflation-adjusted basis, which I think is a very legitimate way to look at it. So you have an industry that's not growing, a market that's not growing, car companies that are not growing. What becomes more important than anything than ever before? Market share. Market share, market share, market share. It's always been important. It is more important than ever before. Because if your pie's not growing, how do you grow your company? You have to do it through market share. The picture that I've got here is of a mobile service that Ford now offers with virtually all of its dealers across the country. Ford Motor Company has got 4,300 mobile service vans, so that if you need an oil change, if you need windshield wipers replaced, if you need new brake pads. As long as the car does not go on a hoist, Ford will send a van out to service your car, wherever you want. It can be at your house, it can be at work. If you take your kids to soccer practice, they'll come out there while you watch the practice and they'll do the work on your car, as long as it doesn't have to go up on a hoist. Now, Ford's at the forefront of this. Everybody's racing to catch up. General Motors, Toyota, Mercedes-Benz, you name it, they're all getting into mobile service. It, by the way, does not cost any more than it does to go to the dealership to get this service done. Why are they doing it? Customer retention. Because if your car is getting serviced very conveniently like this, oh my gosh, you're going to think better of the car company that's servicing your car and helping you out, saving you time. It's all about customer retention. It's not even really about trying to grow dealership service business. It's about customer retention. Why? Because it's back to market share war. You've got to retain the customers you've got and try to get some others. And that means taking them away from someone else because the market's not growing. And affordability is the key to do this. But you can't decontent cars to take cost out, even though that's being done. Once the customer has something in their car, they don't want you taking it away from them. You have to design cost out, not just of the product, but of the process. Our product development processes are way too slow right now. Our sourcing processes of automakers trying to buy parts, components, and services from suppliers is much too slow. All that slowness is cost. It's hindering your time to market. It's hindering your ability to bring terrific new products to the market with the latest technology. Now, automakers are doing some really cool things. Ford's been very open, or certainly more open than any of the other automakers, on what it's doing. This is what they're calling their universal EV platform. It is a radically different way of approaching product development and manufacturing. Back in 1913, Ford Motor Company was the first automaker in the world to start using the moving assembly line, and every other car company in the world had to end up copying it. What's radical about this program, the UEV, no more moving assembly line. The car is going to be made in 3 modules. A front-end module, it's got the tires, the brakes, the electric motor, the steering, the instrument panel. A rear module, it's got the trunk, it's got the rear wheels, it's an entire module. The middle module, the battery pack is the floor, the seats, the carpeting, everything else is in. Those 3 modules are assembled separately. They get put together at the end, and voila, you have a car. No more long lines of people walking down, adding parts to it. That's gone. Ford's taking 600 UAW employees out of the process. They're taking 600 people out of the plant. Now, we don't like to see jobs go away, but this is the way that you design cost out of a car. And what's even more remarkable to me than almost anything is what I said, UAW. Ford got the union to go along with this. Why? Because even the union recognizes that unless this industry in the US gets a whole lot more efficient than it is, there may not be much of an industry a decade from now. Here's another thing that gets to your role in all this, the coatings, and I'm focusing mostly on the outside of the car. I know there's a lot of coatings that go on inside, but I'm focusing more of my attention on what can be done to get the customer interested. And as you guys know, better than I do, black, white, silver. 80% of all the vehicles in the United States, but guess what? This is true globally. But in the US, you know why? 80% of them are black, white, and silver. Even though you all, or many of you certainly, have worked on these beautiful coatings, brilliant colors, great depth of gloss, all the things that you want to really make a car pop, and they don't get ordered. Why? Because dealers are the ones, car dealers order black, white, and silver. They don't want to be stuck with an orphan color. a bright green, a deep blue. Yeah, they might have some red and blues in there, but not a lot. And so how do we get the public to buy what they want, not what's on the lot? And that's what happens. People go in and they've got this idea of how they want to, the color of the car that they want, the option packages that they want. They know what they want. They go into the dealer and the dealer goes, well, look, I'm going to have to order what you want. And that might take a couple of weeks. It might take a couple of months. I'll tell you what, we've got almost what you want out on the lot right now, and I'm going to give you a great discount, and that's what people walk out with. So the most exciting purchase that they make, maybe outside of their home, a brand new car. It's fun to buy a new car. It's exciting to have a new car. You want everybody to see that you're driving a new car. Don't you want to have the color that you want? So how do you get around that? Now, here's one idea. So here's the Ford Maverick. They came out with this color. They called it Area 51. And you'll see a lot of these Area 51 Mavericks running around. Why? Because when Ford did all of its presentations to the media, when it advertised the vehicle, when it had pictures of it in brochures, they used this color. And enough people went into the showrooms and said, boy, I want that color. I think that's cool. That's how you break, one of the ways that you break through it. You make the public aware of what's out there and you create desire. Here's another thing. This is kind of funny. I don't know how many of you know this car. It's the Citroën de Chevaux. This is the Model T of France. This is the Volkswagen Beetle of France. It came out in 1948. De Chevaux, by the way, translates to 2 horses. It actually had something like 38 horsepower, but it was a wild success in France right after World War II. The country's still in smithereens. Nobody has any money. Here comes this very cheap car, 1948. In 1980, the car was still in production in 1980. And one of their designers came up with the idea, you know, why don't we, with paint, highlight some of the styling characteristics of this car? And we'll give it a, you know, kind of a cool name, Charleston. It's kind of a throwback to the 1920s, very famous dance back then. And this Charleston was so successful, so appealing, that it added another 10 years of life to the de Chevaux. No sheet metal change whatsoever, just some coatings, and boy, it changed the look of the car. It gave it more of a jaunty, kind of a cool look. What kind of opportunities might be out there today to do the same thing? Here's another car that I think is a real lesson for the industry. The Dodge Charger and Challenger, these cars came out in 2005. They went out of production in 2023. And how did Dodge keep this old, and most people don't know this, this was actually built on a Mercedes-Benz E-Class platform, goes back to the Daimler Chrysler days, and they developed these cars off it. And so every year, Dodge would come out with a special edition model. They had the SRT, they had the Hellcat, they had the wide body, they had the RT, they had the 392, every single year. Different graphic packages that went on it. And the craziest thing of all, maybe you guys know this story, you see those yellow add-on, clip-on things at the bottom of the front spoiler? Those were there to protect the spoiler when it was going up and down the trucks that haul them to the dealerships, so that it wouldn't scrape or break the spoiler itself. Maybe it would scrape up those spoiler protectors. Well, somehow or other, the owners got the idea that this looked cool. They liked those yellow things down on the front spoiler. The designers in Auburn Hills were pulling their hair out because they thought that this was ruining their design. They can't believe that the customer wanted to keep these protectors on there because they thought it looked cool. But you'll still see them today. And in fact, you can go into the aftermarket. You can buy pink ones. You can buy red ones. You can get any kind of protector that you want there. It became a customizable effort on the part of the consumer. Maybe there's an opportunity to do that because, you know, The tooling for that car was paid off long, long before it ever went out of production. You bet they were making money on that car, but they kept it fresh in the eyes of the consumer. There's other things that have been tried with coatings, the so-called frozen look. A lot of people call this a matte finish. I hasten to correct them. That's not matte, that is satin. And it looks great, and the designers love this. Why? Because the styling accents in the sheet metal look terrific on this car, no matter what the lighting conditions. Direct sunlight above, evening, it doesn't matter. This so-called, the Germans called it frozen. I call it satin. Too many people in the industry call it matte. Matte would be absolutely flat. There's a little bit of sheen to that. That's why it's satin. But the only problem with this is, oh my gosh, is this an expensive paint job? Holy crap. And it's extremely delicate when it comes to cleaning it. If you're washing it and you rub a little too hard as you're washing it, it'll go shiny on you, and then it looks horrible. So what we need are clever ideas like this, but that don't cost much money. And again, there can be a premium, but as long as the automakers don't have to make tooling changes, they can afford to keep an invested product in the market much longer than it has been. Here's the other thing that is the most radical. You guys probably know this. This is the Slate pickup truck, all developed here in Michigan, by the way, in the Detroit area. It'll be out, I think it's supposed to be on sale late this year. Starting price probably in the $25,000 to $27,000 area, but it comes completely unpainted. And they will offer all kinds of wraps that customers will be able to apply to the car themselves. And if you're a second owner, you could take off the wrap of the prior owner and put on whatever you want. I don't know if this is going to work, but it's a very clever idea. It's thinking out of the box. It's trying to do something in a totally different way. And that's what we need to do more of, think out of the box. And we also have to go a whole lot faster. The Chinese are doing all new programs in 18 to 24 months. Typically takes us in the US about 36 to 42 months to do the same thing. It's not like the Chinese are so much smarter or better or anything. Like, they have a better process. I recently talked with Ed Welburn, former head of design for General Motors. He has developed a supercar. I wish I could show you pictures of it, but he hasn't shown it to the world yet, so I can't. But Ed's point to me was, two people did the car, him and a guy who was extremely good at computer-aided design. And he said, John, I used to run the design operations for General Motors. We had 5 design studios all around the world. And he said, me and another guy did this entire car by ourselves. I think there's a lesson in that. I think there's an opportunity to do, and it's being done, but more needs to be done, cheap prototypes, literally cardboard and Scotch tape. I saw when Ford was developing the Maverick. They let me in early to the program to see what they were doing. They were trying to figure out the bed of the truck. It was mocked up in cardboard. And they would bring real live truck owners into the studio and say, what do you think? Is the reach over good enough? Is the length going to accommodate what you want? Does the tailgate work the way all in cardboard held together with Scotch tape? And if somebody said, I think the reach over is a little high, they get out scissors and cut it right now. Oh yeah, that's good. So the whole idea is get the design finalized in cheap cardboard, and once they said, okay, boom, we think this is exactly what the customer wants, then they would mill it out in foam, and then they could start to tool up the whole thing. Move fast, iterate changes, and get suppliers in early. Ralph Gilles, who runs Stellantis Design, told me he wants his suppliers in his design studio at the sketch stage. way before it gets to the RFQ process, way before purchasing gets involved. Some corporate policies have got to change to be able to do that. And what they've got to do is burn the legacy specifications and burn the legacy procedures. All those were developed with the best of intentions in mind, but you know what? A lot of those policies and procedures and specifications go back decades. And a lot of them just don't apply to today. And what I think really works is what I call commando engineering. Small, cross-functional teams working together in the same spot. Things get done a whole lot faster that way. So to wrap up, and I'd love to get into some Q&A too, the car market's not growing. Market share, it's a war, people. Automakers are not growing. They need compelling new products with minimal investment that comes out a lot faster. And there's nothing wrong with this business that can't be fixed with great product. The key is really getting into the customer's head. You know, I showed you those demographic numbers of the different generations. The Japanese automakers in the United States captured the baby boomers' hearts and minds in the 1970s. And they've been riding that demographic wave ever since. Now there's an opportunity to get into the heads and earn the minds of Gen Z and Gen A. And whoever can crack that code and make them desire their product will be able to ride that generational wave for decades to come. Speed's of the essence. You can always hire more people, you can always get more money for a program, but once a minute in your program is gone, it's gone forever. Time is the most precious quality right here. And so thank you very much. That's one of my ideas of what's going on. Okay, I think there's some mics, so.
Yeah, so we have a roaming microphone if you want to ask a question from out here. You can also type in a question on your on the HOVA app, and I think, Jingling, we've already got one, right?
Okay. Here, why don't you go to the microphone?
Yeah, for customer retention, do you think the automotive manufacturers should turn their role from producer and the seller to service provider? How about the growing trend of subscription of cars? How about the growing trend of subscription of car service?
Mm-hmm. Yeah. Well, look, there's a huge opportunity on the service side of the business. I'm told, and I won't name names here, but there was one big legacy company in town that makes 20% of its EBIT, earnings before interest and taxes, 20% of it from service parts. It makes $2 billion a year in service. If they could get their dealers to capture more of the service business, they could sell a lot more service parts and make a lot more money. I mean, billions more. So one of the things that we do in the industry a very good job of is design for assembly and manufacturing. We design cars to go together very easily in the assembly plant, but we don't design them to be easily taken apart. And so when it comes time to service or repair a vehicle or even remanufacture those components, we've just driven up the cost of it. So, you know, I touched on affordability. I mainly focused on the price of a car, but, you know, service and insurance play a big role in affordability for consumers. And if you can make it easier to service a car, you're going to lower the repair costs. If the repair cost is lower, your insurance is going to, well, I'm not going to say they're going to lower it, but it's not going to raise higher. So yeah, service is an incredibly important part, and the same goes for coatings, you know, in a body shop. You know, what can you do to make it faster and cheaper to repair a car? It can, for the automakers, and obviously then their suppliers, there's a lot of money that could be added to the bottom line.
We have a question out here.
Yeah.
Morning, John. Thanks for the excellent presentation. Just a curious question on the Slate product that you mentioned. I think I've seen in the news, and I think you mentioned maybe in the $20,000 to $25,000 price range. Do you think that, coupled with some of the reductions, no paint and maybe some of the lower amenities that would be inside or conveniences, do you think that would fit the market to try to be able to grow back where you were mentioning that we were kind of pricing people out of the market?
Yeah, look, I think there's going to be demand for the slate truck. I think they're going to find a niche. I think people are going to be wowed by, hey, look, it's got crank-up windows. That's so cool. That's not for everybody, but I think they're going to find a segment of the market that really likes the plain honesty that truck represents. But I want to say if I'm remembering right, they have tooled their assembly plant to build 150,000 a year. Ford sells 150,000 Mavericks a year with thousands of dealers all across the country and a great name for trucks. Is Slate going to be able to match that? I don't think so. I personally believe what Slate needs is more models off that platform. So they do have a cap that you can put on the bed of the truck and convert it into an SUV. But what I would like to see is a van version, a stake truck version, maybe a lowered hot hatch version, because all of which what I'm describing there can be done with minimal, absolutely minimal tooling cost. So, and same goes, I talked about the Ford UEV program. There's about 5 top hats that are going to go onto that platform in one plant. And I think that's the key to cracking the code with EVs. If you try to sell 200,000 of them a year, the market, certainly in the United States right now, just isn't going to go for it. Maybe with Tesla, but nobody else yet. But if you can do, let's say, 5 models off that, and you sell 30 to 40,000 of each of those, you filled up the plant. Now you're making money with it. So we'll see how the market responds to the Slate truck. I think they're going to find a nice niche, but it's not enough to get that plant to the capacity utilization they need to make a profit.
There's a question on the app. The question was, will the days of major incentive come back to grab market share or have company learn? Ready to go?
Yeah, I think I got the gist of the question. Look, right now, inventory is tight. And, inventory levels dictate so much of what is spent on incentives. I mean, if a dealer's got rows and rows and rows and rows and rows of vehicles on his or her lot, those vehicles are depreciating. The rule of thumb in the retail side of the business is if a car has sat on a lot for 3 months, the dealer is no longer making any money on it. Because remember, the dealers buy the cars from the car companies, and the car companies give them the financing to do that. So every day that a car or a truck or a van sits on a lot, it's depreciating in value. And so when you start to get close to that 3-month level, dealers want to kick in incentives. Right now, inventory is tight, but I do think we will see some amount of incentives come. I think it'll be more regional. I think it'll be more by segment. But you've got a number of automakers in the US right now who are in trouble. I mean, you look at Nissan, you look at Mitsubishi, you look at Stellantis even. They're highly motivated to get sales boosted. And I wouldn't be surprised to see somebody start tapping on that accelerator of incentive spend, and then the rest of the industry has to follow suit to try to maintain their market share.
Here's a question will resonate with a lot of people. Born the spec.
Yeah.
Yeah, what do you replace them with? How do you address potential liability?
Yeah, well, I'll give you some examples here. And I learned this from my friends at Caresoft, company in town here that does vehicle teardowns, competitive benchmarking. They showed me an electric car, the trunk of an electric car, that had all kinds of sealant where the different body panels match up at the bottom of the trunk in the tire well area. And they said, you know why that sealant is there? It's to prevent any carbon monoxide leaking into the cabin. This is on an electric car. But the specification says you have to put that sealant in there. So they dutifully have adhered to the specifications. Another example relating to electric cars. When the industry went to front-wheel drive transverse engines, it changed the NVH in the vehicles. And so you had an engine that's transverse, that's rocking back and forth as you accelerate, and it's rocking back and forth laterally, and you could feel that vibration in the steering wheel. And for early front-wheel drive cars, there was a lot of customer complaints that, I don't like this vibration. So what the industry did is, go back to brute force, and they put in cross-beam IP supports that are rock solid, and that damped out all of the NVH. So when Karasoff tore down Tesla's car, honest to God, the crossbar beam looks like the shower curtain rod in your bathroom. It's nothing. Why? Because they don't have those secondary and tertiary movements of the engine shaking up front. It's electric. There's almost no vibration at all. But the industry has stuck to putting these big crossbar beams in their cars. So these are just a couple of examples that I'm talking about. And I'm sure you're the experts. I'm not going to tell you guys what to do when it comes to coatings and the like. But what can you do to rethink the ways of doing things right now? I'm not a big fan of Elon Musk, but I do like his first principles approach to everything that he does. And the best example of that is when SpaceX flew rockets into space, brought them back down, and landed them on their tail. I mean, when you all saw that. It was like a science fiction movie. It was mind-blowing. NASA knew that you couldn't do that. NASA knew that was impossible. NASA had tried it before and failed and knew it couldn't do it. So first principles approach is like, why can't you do it? And you start just attacking all the why. Well, you can't do it because it's not stable. Why isn't it stable? Because we don't have the right kind of stabilizer. Why don't we have the right kind of stabilizer? And you just keep attacking these problems one after the other. Now, SpaceX was blessed. They had Elon Musk in very deep pockets. And you all saw rockets coming down, exploding, landing on platforms out in the ocean, falling over. They blew up a lot of rockets trying to figure out, but then they mastered it. And now they can put rockets in space and bring them back for a fraction of the cost of what NASA or anybody else is doing. That's first principles approach. It's attacking every problem from a total physics understanding standpoint when it comes to things like rockets or cars. It can also be applied to processes. Why do we do this sequence of processes? Why are we doing this? Question everything, challenge everything, because the goal is to get things done a lot faster. Another example, this applies to national security. You think the auto industry is slow as molasses when it comes to procurement and getting things done? The US military is way, 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 way worse. And it recognizes this, and it's trying to change it. I saw a speech given by the head of the US Space Command earlier this month, and he was talking about the exact same thing. In fact, I wrote everything down that he said because it applied exactly to the auto industry. And he said, we wanted weaponry in this case, but you could say cars. We want it to be exactly perfect. We want it to do everything the way we want it to do, and so we would write all these specifications to give to our suppliers. We would give them hundreds. We would give them thousands of specifications because we wanted it exactly like we did. And now the recognition is, man, that adds so much time. We're killing ourselves. So now what the Space Force is trying to do is in a couple of simple phrases or one or two sentences, tell their suppliers what they want the outcome to be and let them figure it out. And things go a lot faster. This, by the way, is a key thing that the Chinese auto industry does. Very well-known German supplier, ZF, did a project with a Chinese automaker. This goes back a couple of years ago. And when it's over, they stood back and went, oh my gosh, how do we do this program so fast? We did from walking into the meeting room to first discuss it to start a production in 18 months. We have never moved that fast. How did we do it? And as they dug into it, one of the things that they identified is that the Chinese gave them 500 specifications. And they said, our German automakers give us 20,000 specifications. So I'm just throwing that out there. How do you take that kind of thinking back to the way things are done from a coding standpoint? How can you question and challenge all the procedures that are out there? How can you, using a first principles approach, come up with a better way of doing it?
Yeah, thank you, John. Like another question is relatively straightforward. How is the sales of EV and hybrid? Is it also trending down, or that's actually going up?
Oh, hybrid sales are in extremely high demand. Boy, every automaker in the world right now would love to have more hybrids. Toyota dominates the segment. Honda does sort of okay. Ford's got a few. But then there's not a whole lot of, I take that back, Hyundai, Kia, they're also very big in hybrids. And the beauty of hybrids is, it's very funny. There's a lot of resistance to electric vehicles. Very unfortunately, in my opinion, electric cars have become highly politicized. I can't believe that an automotive technology is part of politics, but it is. If you go back 20 years ago, the same resistance, the same anti-EV sentiment existed back then against hybrid cars. South Park even did a whole program on the Toyota Prius, and it didn't emit smog, it emitted smug, because the people who drove around I'm saving the planet, but it's very interesting to me that the hybrid sentiment has now shifted to EVs, and now hybrids are accepted. You don't have to plug them in. There's no range anxiety. They typically get 40 miles to the gallon or better in cars, and they'll get 30 miles to the gallon in SUV. And with gas price, I don't know, did any of you notice the gas prices driving here today? Boy, they just shot up in the last couple of days, and they're probably going to go higher. I think that will drive even more demand for hybrids. And I also think it's going to get some people who are on the fence about should I get an EV or not. I think this is going to push them over. And the key to watch right now is sales of used EVs, because they are screaming bargains. And I think that's going to pull people in to the EV segment. And I don't think that we're going to see EV sales shoot through the roof or anything, but they're going to start to make a comeback. And
Yeah, here's another
are we
question.
okay? Because we're a little past the time.
Maybe we'll have one more. I think this one people want to hear.
Look, I can talk here almost all day. So.
Right. So about the Chinese EV you mentioned, they offer great features at low price. How should other OEMs respond to that besides hoping for tariffs?
Yeah, look, I have so much respect for the Chinese and what they're doing right now in their auto industry. And my analogy would actually go back to the 1970s. And in the 70s, as I mentioned earlier, the Japanese automakers, Toyota, Honda, Nissan, Mazda, and Mitsubishi and the like to some extent, but the big Japanese automakers captured the minds and hearts of the baby boom generation. And they were delivering cars with very high quality at much lower cost. And Detroit back then was like, they don't pay their people anything, and it's Japan Inc., they're keeping us out of their market, woe is us, we can't compete against a system like that. And then some very astute researchers at the Massachusetts Institute of Technology did a deep dive into how the Japanese do things. They studied the Toyota production system. They wrote a book about it called The Machine That Changed the World. And they didn't call it the Toyota production system. They came up with a new name. They called it lean manufacturing. Because when you went to anybody in Detroit and said, you got to learn how Toyota, you mentioned Toyota, they don't want to hear anything about the Japanese. But anyway, with MIT calling it lean production, the Detroit 3 and suppliers in the region really started to learn Kaizen, how to use end-on cords, how to do quick die change and quick mold change, and so on and so forth. And guess what? They applied those lessons and came roaring out of the end of the 1980s as equally competitive with the Japanese as there was no more manufacturing cost advantage for the Japanese. We need to do the same thing with the Chinese. We need to go over and study what they're doing, and we need to apply those lessons here. There's a lot that we cannot do. The Chinese government heavily subsidizes its auto industry. We're not going to get that. But we are going to be able to do things that they do. For example, China has a government organization called CATARC, C-A-R-T-A-C. It's the China Automotive Technology and Research Center. They come up with specifications for all the commodity products in a car. Tire pressure monitoring systems, windshield wiper motors, door hinges, door latches, fuel filler necks. I mean, the stuff that the customer doesn't care about. And they have commonized that across the industry. And by the way, CATARC also validates the designs and certifies the suppliers. So as an automaker is going to develop a new car, they just pull all these parts off the shelf. All they have to concentrate on is maybe the interior design, some of the technology in the user interface, the exterior sheet metal. This is one of the absolute key ways that they do their programs fast. Commonize components. You get enormous economies of scale because so many people, so many suppliers are manufacturing the same thing. You get enormous economies of scale, but in my book, the more important thing is you get faster speed to market because you don't have to design, engineer, validate, and source any of this stuff. It's already done. Japan has taken that lesson. The Japanese Automotive Manufacturers Association, JAMA, just last month, put out a 7-point program to compete with China. They're getting their teeth kicked in, the Japanese are, in Southeast Asia, a market that they had 80% market share in. The Chinese are taking it away from them. They have identified 7 steps that they need to take as an industry. One of those steps is parts commonization. So how do we compete with the Chinese? Let's go study them. Let's start doing things that they're doing. And we can't do everything. We're not going to get the US government to put hundreds of billions of dollars into subsidies, but we can do an awful lot, like that Ford UEV program that I showed you, that is taking tremendous amount of cost out. I believe GM is doing the same thing or something similar. They just haven't been public about it. But you know, I'll leave you with this thought. In the Second World War, when Fisher Body, which was part of General Motors, had to get into wartime conversion, they adopted a motto: when the strong arm fails, think your way to victory. And that's what we got to do now. Mega dollars and subsidies are not going to get the job done. Doing it smarter is what's going to get the job done.
All right, thanks, John. In the interest of time, we have to stop here. John, we have a small certificate for you. Here. Sorry, it's taking a picture. Yeah.
1 minute.
We have a very short break because this went over a little bit, but thank goodness it was a lot of fun. So we've got, let's take 5 minutes and then reconvene in the track that you want to see. Remember, there's talks in this room and talks in the room down the hall. Thank you very much.
Excellent. That's good to hear.
I like what you said. This industry is very conservative. The spec is every OEM has their own spec. We all are very proud of their own spec. Yeah.
And, you know,
Jichao, it's here. So, laser and then pull it back. So, pretty straightforward.
Okay, folks, if you want to take your seats, start to find a place, we're going to start on our first presentation. Give you a minute to seat. All right, good morning, everyone. You're in the Brian room. We've got two Brians moderating, so we'll try our best to keep things moving and stay out of the way here. So we're going to start with our first presentation about cleanability and paintability study of cast aluminum in the paint shop. And I'll introduce our first speaker, Jichao Li. Jichao Li is a researcher in the Research and Advanced Engineering at Ford Motor Company, focusing on corrosion and surface treatment. Before joining Ford in 2024, he worked as a senior R&D engineer / technical project leader at Constellium. In that role, he led corrosion / surface treatment initiatives for automotive applications, as well as beer and beverage coating projects for packaging applications in North America. Beyond his laboratory research, he also has extensive experience with industrial surface treatment processes and has successfully ramped up a surface treatment production line. He earned his PhD in corrosion engineering from Ohio State University in 2014. So please welcome Jichao Li.
Thanks for the introduction. Hi, I'm Jichao. I'm from Ford. Today we will share our recent work on the cleanability and the paintability study of cast aluminum in the paint shop. For the background, unit casting is being valued by automotive because it can consolidate parts and simplify the process. For example, here there are 171 pieces of the mixed metal highlighted in the body structure. With unit casting, it can be consolidated into just two pieces, the front and the rear. And with these reduced parts, the joining can also be reduced significantly. For example, here there's 1,600 fewer wheels joining. Unit casting can be made by high pressure die casting technology. Normally the molten liquid is injected into the chamber and they can solidify quickly and it takes a few seconds to make one casting. The liquid metal has a temperature like 700 degrees C, and it can potentially react with the die surface and cause some diffusion and make it difficult to release from the die. So lubricant normally applied on the die surface, no matter the cover side or the ejector side, so it can form a protective film. But you can imagine with the contact with the liquid metal, the lubricant can be oxidized and leave some residue on the surface. After the casting process, the part may be machined or trimmed, so there you can imagine there can be some coolant or lubricant. So the casting must be cleaned and maybe sometimes require pre-treatment E-coat. So one typical pre-treatment or E-coat process is we send the part to the E-coat company, and they do the cleaning, pre-treatment, and E-coat and cure. Then the E-coat part is send the send the OEM body shop. They can be assembled with other metal substrate, then pass through the paint shop again. So if you look at the process in the E-coat company and also in the OEM paint shop, they are kind of similar. So we are thinking whether we can directly do the pre-treatment E-coat in the body shop because they have the similar process. And with this new approach, they can potentially reduce, simplify the process and also reduce the cost. But the paint shop process has been optimized to get a better performance on the existing mixed metals. If a new material is introduced, we have to study their compatibility with the current process and then see whether any change is required. So to evaluate this compatibility, we look at their cleanability and paintability in the process. So we look at the edge loss in the alkaline cleaning and also the zirconium pretreatment on the surface. And also more important part is whether the lubricant on the surface or coolant on the surface can be removed during this alkaline cleaning process. Then other pretreatment also put some E-coat to provide good corrosion protection. Normally we evaluate their wet adhesion, also scrap creep performance. In order to evaluate this performance, we needed to have better, look at what's the process in the paint shop and also look at the mouth structure or this new material. Then we can have a better understanding what might happen in the process. So first, the surface treatment process in the paint shop. Here we use an example was stamped aluminum on the surface. Normally you have a lubricant. You also have dirt. You also have some outside, maybe from the heat treatment or from the rolling process. First, it will be cleaned in the degreasing solution. Normally have high pH. It can be hydroxide-based or can be other chemical-based. And also some additive like surfactant to remove the lubricant from the surface. It can be immersion or spray or both. So the purpose of this process is to remove the dirt, debris, or stepping lubricant. Also, so you can get a clean surface, especially oil-free surface. Then you're also trying to maybe control the etching, so you can etch the surface for the subsequent pretreatment. And here we're more focused on the sand film or the zirconium oxide-based pretreatment. This is a key chemical, and also sometimes you see some additives to either increase the coating formation rate or get a uniform conversion coating deposition. So after this pretreatment process, you can get a conversion coating on the surface and the key requirement like the coating rate or the uniformity. Then the pretreated part is sent to the E-coat bus. You can apply a potential and get some polymer deposit on the surface and cured. And you can see here the key process for the new material in the paint shop is the alkaline cleaning and the pretreatment. Especially the alkaline cleaning is the critical step to clean the surface and get ready for the subsequent pretreatment. Now we know what's in the paint shop process. Then we also want to know what's the alloy and especially the mouth structure, because this is we need to talk about both chemical and also the metal alloy to understand their reactivity. And in the cast aluminum normally has a very high amount of silicon. It can be 6 or sometimes can be even higher than 12%, depending on the alloy you use. Because the silicon normally is this in the eutech structure or silicon aluminum phase. Normally it's a layer structure, silicon, aluminum. I want to mention this, so emphasize this phase because we keep talking about this eutech structure. It's a layer structure, aluminum, silicon. The aluminum is still the key element in the alloy, so immediately this in the alpha phase is like a pure aluminum. There are also some other second phase particles like the manganese iron silicon particles. So this is the 3 key phases in the mouth structure. But I also want to mention there are some difference between the top surface and the center because during the solidification, the cooling rate on the surface is much higher, so you may get a fine mouth structure and smaller grains. Another interesting thing you might see is the darkness. So the top surface is darker than the center. So we care about top surface because really the top surface that react with the surface treatment chemicals then can affect the subsequent coating or performance. So now we know what's happening in the paint shop. We also know the mouth structure and also the chemistry of the alloy. Then what happens if you dip this alloy into the pretreatment or cleaning solution. And you may look at, when you look at the commercial product, there can be many different conversations. So here we're just trying to use a simplified metal stability at the pH to get an idea what might happen. And this is solely based on the thermodynamic data, but it can be very useful to predict the behavior of new material in a new system when the information is limited. So you can see, in the alkaline cleaning solution, the pH is normally high, so aluminum can corrode and form aluminate. But if you look at the silicon, it can form a passivation layer, silicon oxide, so it can protect the aluminum from dissolution. So now if you imagine you dip the cast aluminum, which has high amount of silicon, and in the high pH alkaline cleaning solution, aluminum will dissolve, but silicon will passivate on the surface. So this is solely based on the thermodynamic data, but what happened if, let's see what happened on the real cast aluminum that dip in the commercial products. And this is the surface morphology with the cast aluminum at different stage, at the cast condition, after alkaline cleaning, and after zirconium pretreatment, as two different magnification, 3,000 and 10,000. You can see at the cast condition, it's pretty smooth. You may see some small particles over here, but after the alkaline cleaning, the surface becomes very rough and actually showing some porous structure. If you look at the magnification, high magnification, you can see it's a layered structure, and it's mainly silicon. If you remember, so this is more like the U-type structure. It seems the aluminum layer dissolved and just leave the silicon on the surface. Also, you can see some enrichment or the mounted silicon iron particles. And after the zirconium pretreatment, you do see something deposited on the surface, especially if you look at the layer, the gap between the silicon layers is getting much smaller. So it seems there's a lot of etching on the surface, and also we put some zirconium on the surface. And we did further understanding to see how thick was this porous layer and how the zirconium formed on the surface. And so this is the cross-section was a pre-treated sample. We put a carbon on the surface just to protect, to avoid the etching during the annealing process. The red line here is the interface between the porous structure and the metals substrate. There are mainly three interesting things from this cross-section. First, this layer is like around 900 nanometers, and if you convert to the etch loss, it can be very high. The second thing, if you look at the silicon phase, you see this layer structure is continuous from the metal substrate, but the aluminum between this silicon is absent. That meaning there is some selective dissolution of aluminum during the alkaline cleaning process, and they can leave a silicon-rich layer on the surface. The last thing is the zirconium. If you look at this zirconium distribution in the porous layer, it's pretty uniform, but limited by the resolution of the EDS, it's difficult to tell how this zirconium deposited on the surface. If you deposit on the silicon phase or the aluminum phase or both phase. So to have a better understanding about this zirconium formation on this porous structure, we did a TM analysis. So we take a small sample here, and this is the cross-section. And you do see this porous structure. This is the silicon, and there's some porosity under the silicon. And if you look at the zirconium distribution on the surface, back and forth, you can see it's covered almost all the free surface. You do see here the bright dots is artifact during the EDS analysis, so nothing over there. So it seems that the zirconium covers the whole surface, but this alloy the porous structure has very high surface area due to porous structure, so you can imagine the coating rate can be very high. Then now we know what zirconium can form on the surface, but we know in the mass structure there are three phases, so we just take a further look at each phase to see any difference in the zirconium deposition. So first on the aluminum phase, this is aluminum, and this is the zirconium. They're pretty uniform. And this is the silicon phase, is the manganese iron silicon particle phase. Also, it's pretty uniform. Actually, we measure the zirconium thickness on each phase at different locations. Actually, the layer is similar, around 15 nanometers. So zirconium pretreatment has been well studied on aluminum alloy, like a body sheet or extrusion. So we know what happened on pure aluminum, what happened on the manganese silicon iron particles. But there's very limited information about its formation mechanism on the silicon, because based on the current understanding on the zirconium formation mechanism, seems it shouldn't form very thick or uniform zirconium pretreatment on the surface. So to have a better understanding what happened on the silicon phase, how the zirconium form on the silicon, we did a further analysis on the deposition on silicon. So this is the this is a high magnification or the precipitates on the silicon particle. Here is 100 nanometer. You can see this kind of round copper-rich particles. Normally, you do see this a lot in the aluminum body sheet or extrusion, but here you see this on the silicon. But how the copper formed on the silicon phase is a chemical reduction, or is just some hydroxide precipitates. This is something very interesting, and also we get a chance to look at the cross-section of this particle. You see, it's not just on the surface. Actually, it can just directly deposit on the silicon. So this is one thing. The second thing is here, the silicon, there's some area without this copper, and does any copper on the silicon surface, and it can promote this zirconium formation. So we did a line scan from from the silicon phase to across the conversion coating. You can see beginning the silicon is very high, then you see a zirconium peak, and that's the conversion coating. You do see copper peak here, and also another peak outside was the zirconium conversion coating. Then it's really come to an interesting question, why the copper can deposit on the silicon, and what's the driving force for the zirconium formation on the silicon phase. So because based on the understanding that zirconium conversion coating formation is a pH-driven process, and you need a local pH increase to trigger the zirconium precipitates. So there are many now there can be two mechanisms. One is oxygen reduction reaction, so you can oxygen reduce the pH will increase. pH increase will trigger the zirconium formation. Another mechanism is the metal acid reaction. As acid is consumed, the pH will increase, especially this is for the active metal or some coil pretreatment with a strong spray. This metal may be probably more dominant. But silicon is not a strong cathode to support oxygen reduction reaction. Also, silicon also very stable in the acid. So how the zirconium form on silicon? So to have this better understanding, we did a simple test. We instead would do the alkaline cleaning pretreatment. We polish the sample so we can review the melt structure, the eutectic silicon, aluminum, this kind of layered structure, and also review the pure aluminum phase, and then dip this in the pretreatment solution. And if you look at the zirconium, so this white precipitates on the surface, they had high copper and also zirconium, and this deposition pattern match very well with the eutectic melt structure. And if you zoom in this local area, you do see this precipitate is like a layered structure. This layered structure, it can be silicon, it can be aluminum. In our understanding, copper can be reduced by aluminum, then form a copper layer, then promote the zirconium pretreatment. But in this case, it's probably different, because if you look at the EDS mapping of the copper and the silicon, they are pretty similar. If you put these two elements in one map, they overlap very well. This indicated the copper mainly deposit on the silicon phase, but not really on the maybe lower deposition on aluminum phase. I don't want to see no copper on the aluminum phase. So based on this simple test, we think the potential mechanism for the zirconium formation on the silicon is a galvanic is the galvanic corrosion between the aluminum layer and the silicon layer, and the oxygen reduction on the silicon layer promote the local pH increase. Then the copper ions in the solution can form precipitate like copper hydroxide oxide. Then the hydroxide can support a higher oxygen reduction reaction and further increase the local pH and trigger the zirconia formation. Now, just summarize the etch loss and also the pre-treatment on the cast aluminum. So we do see a high etch loss in the cast aluminum, limited by, and we see selective solution of aluminum, and then form a porous silicon-rich mass structure. This mass structure has a very high surface area, and it can allow more zirconia formation. So you can see a higher coating weight. So with this high etching, the decreasing high coating weight, you may see higher chemical usage or higher cost. Then another thing here, we look at the etch loss pre-treatment. Also, there's some lubricant or coolant on the surface. So how they can be removed in the alkaline cleaning solution. So first we did some analysis on what's formed on the casting surface. So the blue line here is the FTR spectrum or the raw lubricant. You can see the hydrocarbon or this kind of functional group. And we also collect spectrum on the black stain area on the lab-made sample. And you see also similar hydrocarbon peak, but there are 3 bumps here or here that's not observed on the raw lubricant or the blue line here. So to confirm what these small bumps, we burn some lubricant in the lab just to simulate the casting process, and then we collect the spectrum on the lubricant sludge, and you do see a similar 3 bumps over here. So on the surface, you may have some partially oxidized lubricant, more like the original lubricant, but you also have some oxidized lubricant, like the sludge on the surface. Then how they can be removed in the alkaline cleaning process. So this is the wettability results on the cast aluminum with a nominal lubricant application. You can see the surface is fully wettable. There's no water-free area, but with excessive lubricant, you potentially can have a lot of water-free area. This can potentially affect the subsequent pre-treatment, also the E-coat performance. So to better understand what really happened on this excessive, this water-free area, we look at their surface morphology change at different stage. So at the cast condition, you can see a lot of black staining. It's mainly rich carbon. And then after cleaning, you see some lubricant is removed. And also, actually, you see a lot of etching under this staining, meaning some etching really goes under the lubricant residue, then still etch the metal substrate. And after zirconium pre-treatment, not much obvious change. This is EDS further showing the presence or the lubricant residue can be very high in some local area. But some interesting that zirconium still can deposit on this carbon, maybe because the carbon is also a strong cathode. So what the staining might affect the performance? Why we care about this heavy staining? So this is the E-coat sample. So this is the cross-section with E-coat panels, and here is the E-coat. This is the metal substrate, and this is the staining, and this is the porous structure we showed before because of etching. You can see the lubricant staining can stay between the E-coat and the metal substrate or the conversion coating. In theory, the E-coat should bond with the conversion coating, not with the lubricant residue. So in certain condition, it can affect the adhesion. If the staining is very thick or very heavy, it may leave some pinholes on the surface. So that means it's not provided by, and no E-coat formation on this area, so potentially some low corrosion performance. We also look at the E-coat performance. So with the nominal lubricant, the wet adhesion is actually very good, and also the scrap creep performance all very good. So they all meet the current specification. With this, I conclude my presentation. So first, the cast aluminum shows a bit of high H loss in the alkaline cleaning and can have some high conversion coating weight, but the performance is robust, especially with the nominal lubricant. If you put too much lubricant, it can potentially lead some staining on the surface, make it difficult to clean in the solution, can affect some adhesion and also cause some defects in the E-coat. And the high H loss in the alkaline cleaning may lead some porous silicon-rich layer on the surface. So last one, I want to thank all my colleagues who support this work, and without their support, it can be difficult to finish all this work. That's all my presentation. Thank you. Yeah.
Okay, so we're ready for Q&A. If you want to have someone read your question for you, you can submit it on the app in the Q&A part, not the chat. And if you are willing to speak, you can just raise your hand and I'll bring you a microphone. So any questions?
Very nice talk, Ji Chao. So I have a couple of questions. So the first question is about the black stain. So after the casting, so it's already become like a dry stain. So is there any method we can remove during the degreasing or the pre-treatment?
Yeah, you have other methods like the plasma laser, or you just use the sand. You can remove that, but the thing is, we see whether we can directly clean this staining in the alkaline cleaning process. So you don't need an actual process to remove the staining. So that's why we're trying to control how much lubricant you apply on the die surface to minimize the potential staining on the surface. So yeah, there are some other methods, but we need some actual process. But instead to do that, we're trying to minimize the lubricant applied on the die.
Yeah, so which means in production, so we want to have robust degreasing. What your suggestion means, probably it's still hard to remove the dry stain during the degreasing, and then the best way is still control the lube before they bake.
Well, yeah, you can, so there's a different way. So you can change the degreasing, but you also need to consider what is other impact on the metal substrate that without staining, and also other mixed material on the body structure, because it will all process together. If you may have a method to increase the lubricant removal, but you also need potentially affect other edge loss or the bare metal without the staining, or the other like the steel or thin coated steel or aluminum structure. So it's not just one simple change to remove the lubricant. You also need to consider the impact on the other materials and also other edge loss, these kind of properties. So.
Nice. So another question is about the copper, the deposition or redeposition on the silicon. So what's the copper content in this cast aluminum alloy?
So this cast aluminum alloy has low copper, it's low copper cast aluminum, and the copper is mainly from, in some pretreatment solution, they may have some additives, so they can potentially deposit on the surface. So.
I see. So the copper is actually from the pretreatment solution and the redeposition to the surface.
Yeah.
Thank you.
Do we have another question? Okay.
I can ask one from the app while we're getting the microphone. It says, what is the thickness of the zirconium oxide in this study, and what is the actual thickness of the pretreatment in manufacturing?
The zirconium thickness. So normally we don't look at the zirconium thickness. This is more like some fundamental study to see how the zirconium deposit on different phases. Normally we look at the coating weight, like we use the SRF to measure the zirconium coating weight. There is some specification, like the coating weight need to be in the targeted range. Too low or too high is not good for either corrosion protection or adhesion. So we normally don't look at the zirconium thickness, more look at the coating weight. So there are some specification defined or validated through some corrosion or adhesion performance. So.
Okay.
Have you looked at the corrosion resistance as a function of how much etch occurs in the alkaline degreaser on the casting?
Yes, we do look at that. And actually, this material is low copper, had very good corrosion resistance. And also here, you may see after even have high etching, the main enrichment on the surface is the silicon. Silicon is a pretty noble element, doesn't strongly affect the corrosion performance. But it may, because this silicon-rich layer is porous, so you can imagine if you have a porous structure between the metal substrate and the E-coat, it can make affect the adhesion. But generally, this material has a very good corrosion performance. But then if you change the alloy composition, you put more copper, iron, or zinc, it can be a different story. So.
Thank you.
Any other questions from online? Anyone else have any other questions I'd like to ask our presenter?
I think for sake of time, we should probably move ahead here. So let's thank Ji Chao for the presentation.
Thank you.
Okay, we are ready for our next presenters to come on up, and I'll do the introduction. So our next presentation is PPG's Sustainable Automotive Paint Shop Solutions, integrating new E-coat and adhesive and sealer technologies. We have two presenters, and I will go ahead and do the introductions. Paula Casino is the Global Marketing Manager for Substrate Protection at PPG. Based in New York, she has over 20 years of coatings experience. A graduate of Penn State University, her career spanned multiple roles in research, development, and commercialization. Her background includes papers and patents in both automotive and architectural coatings. And she will be followed by Lindy Dent, who is a materials chemist with over 7 years at PPG Industries, spanning coatings and adhesive and sealant technologies. She began as a research scientist in surface science and microscopy, later serving as a group leader for next generation sustainable coatings. As a market manager, she now leads the automotive adhesive and sealant portfolio in the Americas, shaping strategy through market insight, technical innovation, and cross-functional collaboration to meet OEM needs. Lindy holds a PhD in materials chemistry from the University of Wisconsin-Madison and has authored 18 peer-reviewed publications. Please welcome Lindy and Paula.
Hello. As everybody pretty much knows us in the room, we're going to go ahead and get started. Today we're going to present on our E-coat and ANS for the future paint shop as it relates to GHG Scope 1, 2, and 3. So how we kind of break this up, we have 4 primary focus areas. Productivity, which is basically your footprint and how big that footprint is and what you can do to mitigate that footprint. Powertrain, we had a great talk with John this morning, kind of talking about how BEVs, HEVs, NEVs, PHEVs are all kind of driving what this looks like for all OEMs, not just Chinese OEMs, moving forward within the paint shop and what the paint shop's going to have to look like to accommodate these. In terms of sustainability, this is obviously a big issue with everybody. And it's going to be something that we talk about when we go through a technology walk a little later on how we have to re-engineer these products from the beginning so that they do reduce your carbon footprint, so that they do meet the 4R standard, so that they do reduce water and waste, even with E-coat, which is 100% efficient, really, but also lowering VOCs and HAPs. I know HAPs isn't kind of a big thing right now in the US, but it's huge in EMEA, and EMEA drives a lot of what we do in E-coat. And then manufacturing and paint shop of the future, which we'll touch on later, and we also have some great colleagues giving a presentation later that's going to talk about even further development as it comes into 3-wet and 4-wet technology. So here's just a few of PPG's recognitions in terms of sustainability. We love Barron's. EcoVadis scores silver. Obviously, we have a little ways to go there. But what we're going to talk about really is the Sustainability Leadership Award. We won it a few years ago on EPIC 300 technology. And what we're going to talk about today is the sustainability next gen of that technology. So in terms of our sustainability targets, we're just going to touch on a couple of these as they relate to my work and Lindy's work. The big one being 50% reduction in scope 1 and 2, 100% reuse, recycle, and recover. Again, E-coat, you can recover most of it, like almost 100% really. 5% annual reduction in spill release. This is a big one for everybody. Reduced water. So we, just like all of our competitors and even our Chinese OEM competitors, reduced water is a huge ask. And we have a lot of people who spend a lot of time just looking at the math of that. What does that mean? What does it mean to us? What does it mean to our customer? What does it mean to the end user? And we'll touch on that a little bit today too. And then one of our big ones that we're always committed to is our 15 million in giving back to communities, as well as our sustainability, which not just Pittsburgh or Detroit, but also our communities where our sites are. So the paint shop and how it relates to scope 1, 2, and 3. So what PPG kind of did is they said, okay, let's assume 70% of our scope 1, 2, and 3 comes from the application and 30% comes from the materials. Where I sit in the PPG value chain, I focus on the materials. So how can I get that 30% reduced? Where does that reduction come from? How do we measure that reduction? And how does the end consumer, OEMs, look at that reduction in their technology? So that's what we're going to kind of talk about today. So I'm going to cover the E-coat section. Lindy's going to cover A&S. So in E-coat, we're basically going to take a technology walk. We're going to talk about how we kind of had to re-engineer our approach, which then requires a re-engineering of the product, which requires re-engineering of the resin. And then we're going to talk about how we move through the value chain of getting the benefit out of the re-engineered process. So in terms of low temperature expanded bake E-coat, where it stands in the can, it still has to be an E-coat, okay? High edge, good throw, good corrosion, pretty indestructible. You can put anything on it. You aren't going to lose adhesion. It has to do what it's always been, but it has to do it better, more efficient, using less water, higher solids, and everything that goes along with that. And then the value outside the can, this is where you're going to reduce your energy consumption, you're going to reduce your emissions, you're going to reduce water usage, and we want faster cure. And we'll kind of talk about the math because we are going to include the math in that, where faster cure means different things to different OEMs. So the product. Basically, we took a technology and we said, okay, it's a great technology, people love it, but we have to make it more sustainable. And because sustainability means different things to different people, we basically have to start from a base. And we want that base to function with the best efficiency we can get. And then we can start delivering additive packages to specific OEMs that have a higher standard. But we want this base to be more sustainable than anything that we've ever done. So we have to give it an expanded bake window. We have to look at a low consumption of solids per vehicle. We have to look at no tin. We have to look at compact process and thin film pretreatment. We have to look at the appearance because we pride ourselves. PPG always prides ourselves on E-coat appearance. And then we don't want to add CapEx. We don't want to slow down your line. We want to give you the ability to speed up your line so you can put more parts on, and then reduce biocide usage. Nobody likes adding biocide on a tank. So from the beginning, we have to re-engineer resin. So in typical e-coat formulation, you basically have a droplet. It hits the panel, it flows, it goes to the bake oven, and you start the cross-linking process. You cannot start the cross-linking process before you've optimized your flow, because if you do, you don't have edge or pinhole coverage, and there's a slew of other things you just won't get. So you're on a seesaw, right? If you're a formulator, we both started in the lab, you have to get off the seesaw. So how do we do that? So we basically changed how the resin is gonna deposit on the film. So we don't want a droplet and then it flows. We want the resin to hit the panel and start flowing, because you're reducing your bake window. You're reducing your bake temperature, which means you're gonna start curing this thing a lot faster. So that's pretty much how we address this from the beginning. And here you can see a traditional or an initial prototype of where we kind of started with this, and you're looking at this, the roughness, where we didn't achieve the flow we wanted before it started to cross-link. So we had to make some changes, and you can see here with our modified resin, you're able to do that. So now you have a flowable material that'll cure when you want it to cure, and you'll be able to get the performance that you want. So what comes next? Your curing mechanism. So to do this, we have to start looking at blocking agents, how they're blocked, when they're released, what temperature are they going to be released at, and then how do they orient themselves quickly. So once you're able to optimize your cross-linker to your polymer, you're able to do your cure test. Now, because we all started in the lab, the easiest way to do this is just solvent rubs. You just sit there and you rub it, and you're like, hey, I've got the cure that I want. But the more scientific way to do it, and to really kind of understand that the resin is doing what you want it to do, we look at rheology and we look at TA. So in terms of rheology, how does it flow? And we always want to make sure that we're maintaining rheology, because our customers don't like when you kind of start messing around with that. That's basic. So how do you achieve the same rheology, but changing your bake portfolio? And here you can see on TA, you can see that your bake is staying pretty much the same, but at a lower temperature, you can achieve the gel content that or the gel rating that you need. So therefore, you're curing this a lot quicker and a lot lower temperature. So what's the benefit to the customer? You get a whole slew of things. You get reduced biocide, you can reduce sanding, which affects bullseye, reduced water, reduced cleaning, your oven filter changes can be less frequent, and no CapEx. And we don't want to slow down your line, we want to help you speed it up. Now, there's not a one-solved solution for everything, and everybody knows it. If you work in production, you know it. So in terms of electric ovens, you're pretty much not going to notice a difference. You'll notice the difference in a gas oven. But what people really care about is the math. So we take a gas oven and we lower the temperature 15 degrees. You'll achieve a reduction of 11%. However, if you reduce your oven time by 5 minutes instead and keep your oven temperature the same, you can get a 13% efficiency. So this becomes really critical to parts, and it's why parts and tiers love this type of technology, because they can just load the line more and they can fill the line. And you can even do this with big parts at your IC, right? So your industrial, your cabs, your John Deeres, they do the same thing. Now we can move to compact process, because this technology fits really well into compact process. So if you're familiar with the zinc phosphates, it's an old technology, but it's a workhorse technology. And if you know zinc phosphate, people love it. But it takes a lot of tanks and it takes a lot of dips. So about 5 years ago, everybody went to the Zircobond, which is like a thin film pretreatment. A lot less tanks, a lot less dips. But the big thing, again, is going back to that scope 1 and scope 2. How do we reduce our carbon footprint? Compact process. We can shrink tanks, we can shrink dips. So again, it's just all part of this system to help everybody achieve what they want to do while costing less and not causing too much chaos in production. So in terms of the paint shop, the solution, we've covered compact process. Lindy's going to talk about the low bank body shop options for A&S. And then we have the commercially available 3-wet and 4-wet processes. And again, our colleagues are going to do an amazing job of talking about their low temperature cure alternatives to these products later today. And I'm going to turn it over to Lindy. Let me shut this off really quick.
Can you guys hear me? Okay, yeah, I sound very loud. That's good. Thanks so much, Paula. So I wanted to talk a little bit today about the work that we've been doing in the adhesive and sealant space, partnering with our E-Coat team to make sure that we can also get that expanded bake cure as well as maintain some of the other performance properties you would want from an A&S portfolio. All right, so I think as all of us are aware, there's a lot more that cures in that E-Coat oven than just the E-Coat, right? So there's also the adhesives and sealants that go along, as well as some other components of the car. So here at PPG, we wanted to make sure we were developing a broader portfolio of products so you could really enable those productivity and cost savings. So within the body shop itself, there's a wide number of adhesives and sealants that are applied before the E-Coat process. Anti-flutter technologies to help with panel vibration for some of those outer panels, structural and semi-structural adhesives, things like that. We have current product lines today, Core-Seal, Core-Bond technologies, but we needed to make sure we were adapting our portfolio and innovating to keep up with these new market requirements and market trends. The higher productivity, the lower bake temperatures that Paula mentioned. We're also seeing some needs for increased manufacturing flexibility. So as we're starting to see new substrates come online, heavier metal segments, especially for electric vehicles, there's new substrates we need to make sure we have adhesion to, but then also we're seeing some more variable manufacturing tolerances. And what I mean by that is that bond line thicknesses are changing, or we're being asked if we can apply things that thicker and still maintain the same performance, for example. So making sure we're taking all of that into account as we're developing some of these new technologies. And of course, with new requirements come new challenges that our technical team has done a great job of innovating around. So I will start kind of talking with our structural adhesives, and then I'll move on to our anti-flutter sealer developments towards the end here. So on the structural adhesive side, we do have an expanded bake portfolio now. Actually, a PPG colleague of mine did talk a little bit about our structural adhesive development work at this conference a couple years ago. And I just wanted to kind of expand upon that, how we've broadened that platform since then, and also moved on to anti-flutters and sealers as well in this space. So for the structural adhesives, this is going to be a 1K epoxy platform, really tailored to meet different strength requirements depending on where it's being applied within your vehicle. So rigid, a crash, or a high crash adhesive, all of those are commercially available. And there were kind of a couple key technical innovations that were required, key focus areas for our team to enable this platform. The first being the reactivity and then the moisture resistance. So on the reactivity side, that's really targeting that low temperature cure. So you need to have a more reactive system in order to get cure at 140 C, 10-minute bake times, if that's your minimum cure target. And you can achieve that with different accelerator packages, right? However, what we found was once you do that, you get a more reactive product, you actually lose shelf stability. So that's not ideal. And so the team has spent a lot of time working on optimizing that accelerator package so you can achieve that low temperature cure while maintaining that long-term shelf stability that you would need. So here I'm just showing a basic graph, a DSC graph showing heat flow versus time. So you're really just seeing, you can change your accelerator, tune that reactivity, or find a balance of reactivity so you can enable those two different properties. On the right side, as we're developing these low temperature cures, we need to make sure that we have the mechanical performance that you would need, right? Both before and after aging. And on top of that, if we're taking into account potentially needing thicker bond lines, especially for structural adhesives, we've seen from typical 0.2 millimeters closer to 1 millimeter. You can see my highly sophisticated graphic showing that as you increase the bond line, you're going to have more susceptibility to moisture. So you really want to make sure you're increasing your hydrophobic barrier, so you're getting more moisture resistance. You get the same mechanical performance after humidity or exposure. And we're predominantly measuring that using lap shear strength, fairly basic technique. I'm sure many of you are very aware, but essentially you apply a bead down with your two substrates, you apply a load across that, and you measure that failure mode, typically looking for a cohesive failure, so failure within your adhesive. And we want to maintain high lap shear strength after humidity exposure with these thicker bond lines, whether or not it's cured at 140 C all the way up through the higher bake window. So just showing with these two innovations, we were able to enable these different properties, and I'll just show some of the data that supports that. So this is our crash adhesive, just showing some of the storage stability that's been achieved. So you can see we have accelerated aging, so that's just tracking viscosity over days of storage at high temperature, in this case 35 C. You can see with that orange curve, that's not what you want to see, where you're seeing a big viscosity climb pretty quickly at high temperature. And we were able to formulate around that to bring it down to more close to that green line, where you have a really good stable viscosity over time. Of course, you want to translate that to real life conditions, so that would be more of a room temperature storage. So we did measure, this is a viscosity versus shear rate curve, just showing performance at 1 week, at 6 months, and at 9-month room temperature storage of the material. You can see very similar behavior between all 3 of these time points, that really nice shear thinning behavior. You would want very minimal increase in adhesive viscosity over the course of that 9 months. So we were able to achieve both heat age as well as long-term shelf stability for this product. On the mechanical property side, I'm just showing some representative data here for our crash adhesive. We also have a high crash that has even higher strength performance, but focusing on the lap shear strength first. So this is looking at a 1 millimeter bead, making sure we have really good lap shear strengths before and after exposure and within our full cure window. It's a little bit of a complicated graph, but essentially we're just showing before and after some optimization. First initially at 10-minute 140C cure times, and then at this kind of more overbake condition at 200C 20 minutes. So you can see in the blue, we had maybe not quite the lap shear strength that we wanted for that 140C cure. We were able to boost that up to above 25 MPa. After optimization, you get a little bit of a trade-off at the overbake condition, but still well within the range that would be acceptable, at least in the bounds of this particular request. And then we looked at a couple of different aging experiments. And without going into too much detail, it's essentially humidity and heat aging cycling. Aged 1 would be after cure, and aged 2 would be looking at heat and humidity exposure both before and after cure, so much more aggressive test. And you see a little bit of trade-offs in that performance as well, but within the noise, I think, and we get good improvement at that, especially at that 140C after optimization for that first aging condition. So while we're doing all that work, trying to balance those properties in the lap shear strength, we also want to make sure we weren't affecting the impact strength, right? Very important for crash performance. This is just a typical impact wedge test you can see on the right. Before and after optimization, we actually were able to improve the impact strength as well with this. So we were not negatively impacting that performance. Okay, so this is a summary then of where we are today with our expanded bake platform. So again, 1K epoxies, we have a range of different adhesives. We have a high crash, a crash, and with a hem flange capability as well as a rigid. You can see kind of the step down in strengths that you can get depending on the specific requirements. For the high crash, just wanted to call out, we've spent a lot of time innovating around that frozen state impact resistance, so at negative 40C, making sure you get above 15 newtons per millimeter strength there. All of these products would have that 140C cure in 10 minutes, minimum bake, with long-term storage stability. Okay, so that's on the structural adhesives, and then I want to talk a little bit about anti-flutters and sealers as well. So we do have a technology platform for anti-flutters and sealers that's rubber-based. It has variable elongation and expansion depending on the specific needs. The 2 major focus areas for the technical team for this development was on the stability, which is obviously related to the reactivity we saw with structural adhesives as well, and then elongation. On the stability side, so we have to enable that low temperature cure, right? So thinking about tuning that accelerator package like I mentioned before, while maintaining that shelf stability. You also need to think about process stability, so that formulation robustness. We really need to optimize the binders as well to make sure we get good process stability throughout that cure window, formulations throughout that cure window, and then over time as well. And that just comes down to, in a lot of ways, binder molecular weight. So can we tune different binder molecular weights to achieve that kind of stability that we need? On the elongation side, so thinking about flexibility and ductility, how do we adjust that depending on, again, the need, specific need, the location of where it's going to be applied on the vehicle, if you need a more of a sealing functionality versus like a high elongation functionality or a gap filling functionality. And really you can achieve that by adjusting the polymer microstructure. So just showing a very basic chemical structure here, but you get the idea, where we can adjust that microstructure to tune that elongation. And we're primarily measuring that using a standard tensile test with those dog bones, where you pull them apart until they break. And we've developed this tunable portfolio where you can tune that elongation to meet varying requirements. So just to show a snapshot of some of the mechanical properties of this material, of these anti-flutter technologies. So pressure versus flow. So this is a graph showing pressure versus flow for our standard bake formulations, as well as this expanded or low bake technology formulation space at both 2 weeks and 6 months. And you can see that the performance is very similar for pressure versus flow. And that's very important for anti-flutters, especially when you need to have very consistent and tunable shape stability. So you have a very specific diameter and height of your droplets that you might be wanting to apply, making sure that's very consistent over time. And so we're able to achieve that. And then on the elongation side, so this is just, again, that tensile test I mentioned, so we're showing strength versus elongation percent. You can see our initial formulations, we were maybe in the 20% elongation range, able to tune that up to 80 to 100% elongation, depending on the specific technology. So we were able to get that improved elongation, but while maintaining that good process stability as well. So just to summarize, we do have a full expanded bake portfolio now, so core bond structural adhesives, semi-structural hem flange, as well as our core seal anti-flutters and sealers, all of which can achieve that expanded bake window with that minimum 140C cure in 10 minutes and 6-month storage stability. And some other properties I didn't go into detail today, but that obviously are important too, would be sag resistance, corrosion resistance, multi-substrate adhesion, and then robotic application. So all of these products partner well with our new E-coat developments to help enable those costs and energy savings that Paula mentioned in her part of the talk. Okay, so I just wanted to wrap, just kind of summarizing, Paula introduced all these market trends and drivers that we're looking at and developing around, and I think our E-coat and A&S expanded bake solutions really tie into a lot of those today: productivity, powertrain diversification, sustainability. But I wanted to also tease kind of what's next. And so thinking about that paint shop of the future, all the buzzwords, modular assembly, mega casting, giga casting, et cetera, making sure that we're positioning our portfolio to help enable those newer manufacturing processes. So we are looking at new solutions there. So we have a variety of ambient cure adhesives and sealants, some of which are commercially available, some of which are under development, that I wanted to just mention. Again, within our core bond structural adhesive product line, thinking about maintaining impact and shear strength that you would need with that ambient cure. And then we have a core seal structural sealer that we are working on, which would be balancing strength and elongation, so high strength and high elongation. So happy to talk more about that offline if that's of interest, but wanted to throw that out there. And then on this more substrate protection side, we do have a new aluminum pretreatment line that's specifically designed to improve efficiency within aluminum pretreatment space. So as we're starting to see more aluminum parts come online for lightweighting and other things, we have a product line that can help enable that as well, predominantly for our tier segment. So that's all I had. So I think thanks so much everybody for listening, and happy to answer any questions.
Okay. Again, if you want to submit your questions on the app or raise your hand. Any questions for Paula and Lindy? Okay, I'll get us started. Did you guys face any challenges? So you've got two developments happening. You've got your E-coat development and your adhesives and sealers, and they have to play nice with each other, right? So how did you handle this kind of parallel path where you got to make sure that you're not formulating an E-coat that can't tolerate a little bit of contamination from those sealants and vice versa? So were there any challenges with that?
Yeah, so I think I can start, Paul, and if you want to add. So I think PPG's well positioned there, right? So we have all the layers, and I think that's a big advantage. So we have our Coatings Innovation Center in Pittsburgh, where all the folks sit right next to each other, right? They're all in the same building. I worked there for a number of years, and I think that's a big strength. So our adhesive and sealants team can walk down the hall and say, hey, what are you doing in E-coat? What's your latest test results? Those types of things. Of course, you always have to make sure you're doing that, regularly checking in, keeping up with the new innovations, but I do think that we're well positioned to handle that. And then as we're seeing new challenges emerging, constantly reporting out to the team so we can take that back and say, okay, they're seeing a change in E-coat, how does that impact our A&S? Do we need to make a change to accommodate?
I'll do one online more. Are you looking at going even lower in process window for E-coat, whether by reducing curing temperature or bake time or both? And what are the main technical limitations?
Yes. And to Lindy's point earlier, we have to keep, anytime we go lower, Lindy is usually my first phone call. Because again, to her point, it's a process. So if I go in and I say I want to go down to 130 because we have a customer who wants to go to 130, and that is a big market trend right now, her A&S has to do that too. Or if we don't have that communication, then think of it as a process. We have to add ovens, right? Because then you have to cure them at different temperatures, and we don't want to do that. Our customer doesn't want to do that. So for us to go to 130 first, I have to consult A&S, and then we have to look at the resin, because again, what can we get out of the resin? What can we get the resin to do? How do we get it to cure by still being able to flow? We don't want to add a lot of additives because that adds cost, and that adds a problem with our Chinese OEMs. So yes, everybody wants to go to 130, and at some point we'll get to 130 and they want to go to 120. We'll get to 120 and everybody wants 80 to 90 for a 5 wet, right? That's what we do. But I think we're in a really good spot right now. I know we're not able to talk about it, but I think we're in a really good spot. I know A&S, and we have weekly meetings about it now. So yes, we're going, and we'll probably have a lot more to talk about it in Focus 2027.
Thank you for interesting work. So I'm from the aluminum supplier, Constellium, for OEMs. So we supplied a lot of aluminum sheet for the structural outer applications. So we are also monitoring this research and development in the PPG. During the curing of PEMPIC process, aluminum substrate also experience the change to meet a mechanical target. So it's an essential step for aluminum structure. So have you, this is a part of the consideration when you are like lowering the curing temperature? So for aluminum, from 180 degrees C down to the 140 degrees C is a huge change in the mechanical property. So so we are interested so how to have OEM to adopt this technology.
So OEMs, and I'll speak from the eco side, and then I'll let Lindy handle A&S. We already have a lot of OEMs that are already pushing to 140, right? And I'll be honest, from an e-coat perspective, it's a lot easier for a line to handle 100% aluminum than it is mixed metal. So we see the issue a lot more on tiers, where a tiers line used to be, 100% carbon. And then all of a sudden it went to 80, then 60, and now you're down to 40 because they just keep packing more aluminum. And what happens is it generates a lot of sludge. So that's why a lot of our aluminum products, usually our pre-treats, our new technology that's more centered on aluminum, will go to tiers first, and then we'll move it over to OEM. And that's very deliberate because it's a lot harder in tiers because they do a lot of mixed metal lines. But when you have a straight aluminum line, it's a lot easier to manage because you don't have this continuous sludge generation that has to be dealt with. So it's a little easier on the OEM side to go to lower temperature than it will on tiers.
Yeah, I'll just add, and I think, Paul alluded to this too, is one thing that we are seeing for current customers a lot of times is they're not actually dropping the temperature. They're just increasing their line speeds. And the lower broad bake window helps prevent cold spots, for example, of the adhesive. So you get full cure at the low temperature, or make sure if you have a heavier metal segment, you're still getting full cure of your adhesive or your eco technology at the faster line speeds. And that is due to the complexity of things like other things that have to cure in that oven, like baffles and bake hardened metals and things like that. So we're seeing innovation in those spaces as well, but that's why I think we're seeing more of that higher throughput as being the initial push for this.
Okay, we'll ask another one from online. Industry has moved from 2K adhesives to 1K, but is there anything that formulation chemists could achieve again with 2K adhesives for an expanded bake e-coat to an actual low cure e-coat for future throughput? So, yeah. 2K versus 1K, let's start there.
I used to make 1K. Do you want me to answer that?
Yeah, you can. Let me give a start, please add in. Yeah, so I think for PPG, our focus generally for oven-cured systems, we're focusing on 1K technologies. There's a lot of simplicity in equipment, right? With a 1K versus a 2K, it's a technology that's tried and true. We believe it can reduce the temperature and still get good performance. For like an ambient cure, though, now we are thinking 2K, and there's a lot of complexity there, right? In terms of new equipment, making sure you have the right mix ratios. But we believe that 2K, you have a little bit more control over the reaction than you would with like a moisture cure 1K, for example. So I see 2K more for like an ambient cure type technology system, which would be for maybe a more disruptive type manufacturing practice, or if you need more plastics on your line. So I think that's kind of where we would position our portfolio. Hopefully that answered the question. But Paula, if anything else to comment.
From like a 1K, and I know you and I kind of joke about it a little bit, 1K is dominant in a lot of areas except automotive. Where you have construction moisture cure 1Ks, and now people are making a polyaspartic 1K, right, modified. I always call it SPAR, because I'm not going to call it a spur, because I think of something else when I think of that. So to Lindy's point, we'll get there, and I think it just is going to depend on what technology or what chemistry is adopted to get there by us and our competition.
Okay, another one online. Is there an impact on target film thickness with the Epic Low Cure E-Coat product?
So we actually have a wider range because our friends in EMEA, I'm global, so I have to worry about everybody. Our friends in EMEA have their target is much lower than what I call ASCA, America is. It's about half. So the range, like 35 to like a standard. We have some OEMs that want to go down to 30. We have one that's like, can we do 28? So we're even looking at that. So we're going to go pretty low on this product if we can, which we will.
Other questions? Okay.
Yep. Yeah, let's go ahead and thank the speakers.
Thank you so much.
Thank you, everyone. A reminder that we have a break now, so please take an opportunity to go see the student posters over in the other room, and we'll reconvene back at 10:45. Please come back before 10:45. Thank you.